In our final section of Chapter 6, we're going to be revisiting our binomial distribution, but we're going to see how we can use a normal approximation to the binomial. Remember that normal distribution, that's what we've been working with all chapter. So now we're going to see how we can relate our binomial distribution to our normal distribution we've been working with. So just a little recall about the binomial distribution. Little recall for you. We have a fixed number of trials. The outcome of each trial is independent. Each experiment only has 2 outcomes, or if you have more than 2 outcomes, you can group them so they're just down to 2 groups, so 2 different outcomes. You can regroup them. The probability of success is the same for each trial. So one trial happening, the result of that trial does not affect the next trial's probability of success, or the one after that, or the one after that. Each trial has the same probability of success. So just a little recall, we visited the binomial distribution last unit. So now, when can we use a normal approximation to the binomial distribution? When your probability of success, and remember we denote that with that little lowercase p, when it's approximately half, and as we've seen n represent a couple things. N has been our number of trials. N has also been our sample size. So in either of those, whatever situation you're looking at, whether you're given a number of trials or a sample size, as that number increases, the shape of our binomial distribution will become similar to the shape of the normal distribution we've been using. Now you might be thinking, okay, Miss Galley, so how do I know when it says the probability of success approximately a half? Well, what's close enough to a half? Or as my sample size or number of trials increases, well, how do I know? How do I know when it's increased enough? How do I know those things? So how do I know when I can do this? Here's how you know. Your normal approximation can be used when n times p, so number of trials, or your sample size, whichever thing you are given, your sample size times your probability of success, sample size times probability of failure. When those are both, and it has to be both, are greater than or equal to 5, that's when you can use our normal approximation. That's when you can use it. So you don't have to do any kind of guessing at all. It's very cut and dried for you. Here's when you can use it. Now, since it is going to be a normal approximation, the binomial distribution will be approximately the same as our normal distribution. So to be able to use the normal approximation, we have to use certain boundaries for x. This little table can be found on page 355 in your book. And yes, I will tell you now, this table is not on your formula card that you will have for your test. So do you have to know these? Yes, you do have to know these. The best way to get to know them is by doing the practice. The best way to get to know them is by doing the practice. There's only a few cases there. And your only options are adding a half or subtracting a half. So figure out when the cases are that you need to add a half. Figure out when the cases are you need to subtract a half. Just group them into 2 categories. Okay, so working with them, that's the best way to get to know them. These formulas, though, the mu, which is your mean, and little lowercase sigma, which is your standard deviation, those things will be provided for you on the card because they are from the binomial distribution. So those formulas are the same. This procedure table you can also find in this section as well. And we will go through this piece by piece in a couple examples together. Step 1, though, if you did write this out in your outline, step 1, you just might want to make a little side note what step 1 means. It means you need to check to see if n times p is greater than or equal to 5 and n times q is greater than or equal to 5. That's what step 1 means. That's what step 1 means. Check to see if you can use it. That's when we're taking our sample size times probability of success and sample size times probability of failure. They both have to be greater than or equal to 5. If one is not, then you can't use this. You just have to stick with the binomial distribution. Step 2, find the mean and standard deviation. Those formulas are the same as they were for the binomial distribution. Those formulas will be on your formula card for your test, but they are in the Chapter 5 section. They're with the binomial distribution. They're within the binomial distribution. Step 3, write the problem using probability notation using x. Probability of x, and that's going to be kind of a fill in the blank. Do you want x equal to a number? Do you want x less than a number? Do you want x greater than a number? It's kind of a fill in the blank from there. Now, when you're going to use step 4 says rewrite it using your continuity correction factor. So again, because we're using a normal approximation, the binomial distribution does not match perfect with the normal distribution. So we have to have that continuity correction factor in there. So that table, if you need to, was on page 355. Find the corresponding z-values. We're just looking for just a plain old z-value. We're not looking for a sample mean. I know a lot of us are used to sample mean. We just did central limit theorem concerning with sample means. Now we're just back to data value minus mean divided by standard deviation. So once you can figure out step 1, can the normal approximation be used? Once you figure out yes, mean and standard deviation, those are formulas we're already familiar with. Probability notation, you should be okay with that. If not, we can get a little practice with that. The continuity correction factor, those are going to take some practice, definitely. So this is going to be a step that's going to take some practice. Step 5, though, finding the z-values and finding the solution, those are things we've been doing the entire chapter. So those things should be okay. So let's try this. According to the government, 5.3% of those employed are multiple job holders. In a random sample of 150 people who are employed, what's the probability that fewer than 10 hold multiple jobs? Now, I know for some of us, our big question is always, well, Ms. Golly, how do I know when I'm going to use this? How do I know when to use this versus the other things we've been doing in this chapter? For this one, we know we're given a specific percent. And I know you're thinking, well, in other questions, Ms. Golly, we're given a specific percent. We're given a specific percent, and we're given a sample size. Now, I know when we did things with the central limit theorem, which was our last section, I know we also worked with samples. But in this question, though, there's absolutely no mention of a sample mean. So that's what separates what we did with central limit theorem from what we're doing with the binomial distribution. We're not looking for a sample mean in this. We're looking just that fewer than 10 hold multiple jobs. We're looking at a specific data value, but we have a sample size. So that's what's going to set it apart from even what we initially did with our normal distribution. We're given a sample, and we're just looking at a specific data value. We're not looking at a sample mean. That's going to be how I know to do this versus central limit theorem, which was last section. That's how I'm going to know. So what I want to do is that procedure table we just looked at that I filled in a few extra pieces for you. I want to go through that step by step. I'm going to label each step up here so then you can kind of pinpoint maybe some steps that you're unsure of or what those steps actually meant when we just walked through them in the procedure table. So step number 1 says, hey, I've got to check to see whether or not I can even use the normal approximation. Step 1, you can't skip. Step 1 is super important. So let's just jot down, we need to know N, we need to know P, and we need to know Q. I'm just going to jot those down. Before we even dig into step 1, I need to know those things first. N is your number of trials or your sample size, same thing. So in this case, we have a sample of 150 people. Probability of success. Now I'm looking that they hold multiple jobs. So 5.3% hold multiple jobs. So that's my probability of success. I want to make sure that the data value I'm looking at, the description of it, matches my probability of success. So 10 that hold multiple jobs, 5.3% are multiple job holders, so those things match. To find your Q, remember P plus Q should equal 1. So just do 1 minus your 5.3%, and we get 947. Step 1 says we need to make sure that N times P is greater than or equal to 5, and the same for N times Q. So let's fill in the blanks here. We have 150 times our 5.3%, and we get 7.95. So that checks. That's greater than or equal to 5. And then we have 150 times our 94.7%. So even without doing the actual calculation, we should be able to look at that and know, yeah, that's definitely bigger than 5. Almost 95% of 150, that's definitely going to be bigger than 5, but the exact value, if you want, is 142.05. So step 1, check and check. Now we can continue. If one of those didn't check out, then the question is, so what would I do? Then you'd have to use the binomial distribution that we did back in chapter 5. Then you just have to use that. So since it checks out, we can do our normal approximation. Step 2, you want to find your mean and your standard deviation. The mean we actually already found above, but I will rewrite it here. Just checking in step 1, having to do N times P to see if it's greater than or equal to 5, you've actually found your mean as well. So you really don't have to redo that for number 2. I just label it as my mean. Standard deviation, we do actually have to do that one. It also, guys, if you want to take a little shortcut here, it includes N times P, that first part. So if you just want to put 7.95 in there, you can. And we get roughly on this one, we'll go 2.74. All right, step 3 for us. Step 3 says we're going to write probability notation. Capital P, that's our probability notation. And in this case, we want fewer than 10. So we want our data value to be less than 10. Fewer than 10, so we're not going to include 10. That's all we need for step 3. Writing step 3 is then going to help us with step 4, which is where we have to throw in our continuity correction factor. So we have to figure out, are we going to add a half or are we going to subtract a half? So if you need to, there's absolutely nothing wrong with. It's going to take some practice for you guys. Looking at that table, I don't expect you to have it down already. Hopefully by the time you're done with the practice, hopefully you've got a pretty good feel for when you're going to add a half versus subtract a half. We're looking at, we have case number 5 here, our x value being less than a number. So the correction factor, we're going to subtract a half from our value. So we're going to have x is less than 9.5. Step 5 says to find our z value. And all we're doing, guys, I wrote this down on the procedure table there, it's just our plain old z-value formula. We're not looking at a sample mean. We're just wanting to see if fewer than 10 hold multiple jobs. There's nothing about a mean mentioned. We don't have to do anything with central limit theorem. Now the x value that we're talking about, we have to use the x value with the correction factor applied. So my data value is 9.5. The mean we came up with was 7.95. The standard deviation we came up with was 2.74. So we end up with a z-value roughly of 0.57. Steps 5 and 6, guys, it's what you're used to already. We've been doing this since the very beginning of this chapter. When we have a z-value, now we just have to find that area. So we have a z-value. I'm just going to do step 6 up here, actually. I'm going to draw my picture. Positive 0.57 will be off to the right. And it says we want fewer than 10, so we're going to shade to the left. The left areas for the table people, these are the ones you like the most. When you look up 0.57 as your z-value in table E, the area you get is the area you get to use. Calculator people, you probably don't have a favorite. You have to enter a lower and an upper boundary anyway. So you might not have a favorite, really, calculator people. But table people, areas shaded left. Those are always the easiest ones. So really, once you hit steps 5 and 6, that's nothing new for us. Step 2, those are from the binomial distribution. So really, the new ideas for us is having to check to see if we can use the normal approximation. And probably the thing that you're going to have to focus on the most is getting those correction factors down. It's probably going to be what you have to focus on the most. Let's stick with this same opening here, the same problem situation. But let's take a look at more than 50 are not multiple job holders. Here's where you have to be very careful. My N, I'm still choosing 150 people. But now my P, my probability of success is no longer the 5.3%. Because now what I'm looking for is that they are not multiple job holders. So a success for this situation is that they are not a multiple job holder. So the probability of success for that is going to be the 94.7%. You have to look at what characteristic are you wanting your data values to have, and then you have to go with the percent that matches up. So P and Q in this case are flip-flopped from part A of this example. P and Q are flip-flopped. Now flip-flopping P and Q though, step 1's already done. N times P, N times Q, it doesn't matter that P and Q are flip-flopped. It's going to be the same as last time. What does change though is when you go to find your mean. Your mean is N times P. So now this becomes 150 times 0.947. Which we found this for part A when we did our check for step 1. Standard deviation though, guys, that's not going to change because it involves multiplying N times P times Q. So interchanging P and Q will not affect step 1. It will not affect your standard deviation. So save yourself some time on those things. Step 3, probability. We want our data value to be more than 50. Correction factor. I am just going to take a little flip back. I want to make sure you see how to use that table. So now this time, we're looking at option 3. X is greater than a number, so we have to add a half onto our value. Remember, our only options are adding a half or subtracting a half. So it probably won't take a lot of practice for most of you to get down when you need to do each thing. Finding Z. Remember, the data value you use is from the correction factor, or it has the correction factor already used, divided by our standard deviation. Now I know whenever people do this one, they're like, wait, Miss Golly, whoa, this can't be right. That's way too big to be a z-value. Well, when you get a z-value that big, or actually that's really small, I should say, when you get one that small, I mean, that's going to be sitting like way, way off to the left. And we want to know the probability that more than 50, so that means we're going to shade to the right. So what are the chances that more than 50 are not going to be multiple job holders? They're going to be really, really good. Now I can't say 100% because remember, one of the properties of this distribution is it's never going to touch the x-axis. So it's never going to totally cut off. So how do we handle it for number 6? Now, in your calculators, if you're a calculator person, you enter this in and you get 1. But just remember, we have to think about our property. This distribution never touches the x-axis, so there's never a point where it completely shuts down. So, if you're a calculator person, you'd say approximately 1. Okay, and that's okay, but I want the approximately in there. Because if we say the probability is 1, if we put that at equals 1, that means there's 100% chance it's going to happen. That it's absolutely certain to happen. And this may or may not be. This may or may not be, okay? Now, if you're a table person, this is a big reason why I chose this example, is if you're a table person, if you look in table E, it says, and you go to the negative sign, down at the very, very bottom, and it's in very tiny print, I wish there was a little bit bigger print, it says for z values less than negative 3.49, use 0.0001. So in table E, the area to the left of negative 33.41, they tell you to use 0.001. So anytime you get a z-value smaller than negative 3.49 and you're a table person, the area to the left is 0.0001. So to get the area to the right, we're going to do 1 minus, which will give you a lot of 9s. So is this approximately 1? Yeah, if you're a table person, I would take all the 9s, or if you wanted to put approximately 1, you sure can. Just keep in mind, if you put an equals 1, you're saying that it is absolutely certain to happen. So just be very careful on that. Okay, be very, very careful. Your next task, guys, I want to give you guys a chance before I give you the assignment, before I turn you loose for work time. I want to give you guys a chance. I'm going to put a problem situation up for you, and I am going to give you the solution. I want you to try out all 6 steps. If this is not the solution you come up with, I want you to raise your hand so I can look at your 6 steps. So jot something down for these. Even if you're not going to jot a whole lot down when you do the practice, jot it down for this. So if you don't come up with that, I can take a walk through your 6 steps and see where maybe you're getting a little bit stuck, or maybe you made a small mistake somewhere. So try this out, guys. Once you're able to get this particular answer, go ahead and start in on the practice. The rest of the time is yours to work and ask questions.